Okay, this is a physics video off of chapter 23, and it has to do with analyzing circuits. But the circuits we're going to do are going to be combined series and parallel circuits. And what has to happen on these problems is that we have to simplify the circuit down to a single resistor, voltage, and current, and then work backwards. And I'm going to show you a couple of examples. I have a handout that you're going to end up trying to work on or working on, and then there'll be questions, I know that, on this one because it can be fairly tricky. But let me take you through a couple of examples, and I'll explain what I mean. Let's say that we have a voltage of 24 volts. We have a parallel network, and then we have two series resistors. Okay, and this resistor we're going to call R1, and it is 12 ohms, and this is R2, and it is 6 ohms. And this is R3, and it's 5 ohms. And this is R4, and it is 3 ohms. What you're going to end up with, I'm going to do it over here, is you're going to be asked at the end of the problem, what's the current through I1 and the voltage across I1? The 1 stands for the resistor. I2, V2, I3, V3, I4, V4, and finally, R total and I total. And remember, our basic equation is V equals IR, or R is equal to V over I, or I is equal to V over R. Those are our equation that we're going to work with, plus what we would do with parallel and series. So here's the first thing. When I say simplify, we're going to take any parallel network, and we're going to figure out what that resistor actually is. So if you do 1 over R total is 1 over 12 plus 1 over 6, you will find that R total is 4 ohms. You can do that yourself. So this is then 24 volts. And what I'm going to do is mark this now as R1 plus 2. Or actually, R1, I usually do R1, comma 2, and it is 4 ohms. And this is R3, 5 ohms, and this is R4 at 3 ohms. And now we're going to simplify one step further. And we're going to put, again, 24 volts, that's not changing. This can be thought of as one resistor, which is R total. And it is 3 plus 5 is 8, 12 ohms. So now we can come over here and we can say that our R total is 12 ohms. I total is voltage divided by R total. So since this is 24 volts divided by 12 ohms, there will be 2 amps flowing through it. Okay, and now we need to use some thinking. If you were to think of this as water, the water is like the current. Think of gallons per hour is what a current would be. We have 2 amps that are going through these two together. 2 amps going across here, 2 amps going across here. In other words, all the water has to pass through that rapids, all the water has to pass through that rapids, all the current has to flow through this resistor, all the current. So you can come over here now. I don't know why I put that so close. And I know that this has to be 2 amps, and this has to be 2 amps. And 2 amps, kind of out of the, well, you don't need to see me. 2 amps times 12 ohms. No. Remember that I4 here was 3 ohms, and this was 5 ohms. And 2 times 3 would be 6 volts. In other words, voltage is current times resistance. 3 ohms times 2 amps gives me 6 volts. 5 amps, this would be 10 volts. And what is happening is, as the electricity flows, it has a voltage drop. Well, now the last one, you say, well, we've got a problem because the current can split apart. Yes, it can, but come back to here. What's the voltage drop if I was to put a voltmeter here across that parallel network? Well, it's the same as putting it across here. And since I know what the current is, the resistance for R1 and R2, that's 4 ohms, times all 2 amps have to flow through that. Both of these have 8 volts across them. And now, since I know that this is a 12 ohm and this is a 6 ohm, you're going to find that this is 8 divided by 6, that's 1.3 amps, and this would be 0.6 amps. If you add these two together, it'll give you 2 amps. If you add all these together, it'll give you your 24 volts. Each one of these networks should be 2 amps. And that would be analyzing a simple series parallel circuit. You may not look at that as being real simple, but it actually is in comparison to what it could be. Okay, so let me do a second one. And I'm going to erase that. And for simplicity, let's just do this because we tend to do the same thing. I should have left that up. Let's say that we have this circuit. We have, let's do 12 volts this time. Doesn't matter what this is, but you can do this so you end up with nicer numbers. Let's have 125 and 20 and a 40 and a 10. I'll mark it here in a second. So R1 is 100 ohms and R2 is 25 ohms and R3 is 20 ohms and R4 is 40 ohms and R5 is 10 ohms. Okay. And our first step will be to combine these together. So if we do that, we're going to have 12 volts again. And I've already done this, but if you do 1 over 100 plus 1 over 25, you end up with R1 and 2 as being 20 ohms. And R3 is a single one, is 20 ohms. And R4 and R5 R4 and R5 end up being 8 ohms. Okay? And because of that, I can go one step further now and rewrite this all as a single resistor. Our total is going to be 20 plus 20 plus 8, 48 ohms and 12 volts. And so coming over here now, and by the way, I need to add one more, I5 and V5. And you're going to have to find out what our total is. We know that now, 48 ohms. And I total, and we will know what that is. That is 12 volts divided by 48 ohms. And that would be 0.25 amps. And now because of that, and watch, because this is important, I can figure out what the voltage drop across each one of these will be. Voltage is IR. All the current has to throw through this 20 volts, 20 ohms, so it's 0.25 times 20. 0.25 here, also times 20. 0.25 times 8. And what you will get is 5 volts, but that would be across I1 and I2. V3 is also 5 volts. And 0.25 times 8 is 2. Right? 1/4 of 8 is 2. 2 volts and 2 volts. Now, if you add, you say, if I add this up, I get more than 12. But what you're really doing is adding those, that, and that. It's 5, 5, and 2 adds to my 12 volts total. And now you can simply work backwards. This is 100 ohms, 25 ohms, 20 ohms, and this one was 40 ohms and 10 ohms. And 5 divided by 100 would be 0.05 amps. And this would be 0.2 amps, 25 divided by 25. This one, all of it has to flow. 5 divided by 20 is 0.25. And this one, 2 divided by 40, we actually end up with 0.05 amps and 0.2 amps. It's kind of interesting if you look at these two and these two, they add to the same thing. They give you 0.25 amps. That's because our current is splitting. Most of it's going this way, some of it's going here. But notice this ratio of 100 to 25 is the same as 40 to 10. And that's why this ratio and this ratio are exactly the same. So I could keep going. And I can certainly help you with my office hours if you're going to have trouble with it. Or if you have trouble, I could make 10 parallel networks. We could do a parallel network where instead of 2 here, you had a third one across here. It really wouldn't change anything. We're still going to work it down to here, work back to here, figure out what the voltage is across each one of these networks. The voltage across 1 and 2 was 5. The voltage across 3 was 5. Across 4 and 5 was 2 volts. And once you know what your resistors are, you can figure out what the current is. And that is the way that that circuit is analyzed. I have a homework for you, but it is 2 handwritten pages. And I have copied them off, and I will put them in. I'll name them Analyzing Circuit Handout. Page 1 and page 2. And I will get the answers up to you as well. I'll do that fairly quickly, but I will get this up and that page up, and then you can work on both of those. All right. So that's a pretty quick lesson on resistor networks, but that'll get you started, and then we can talk more about it later. All right. And that, by the way, is the last assignment before the Easter break. So we'll talk more tomorrow.